Okay, so now let's talk about vectors. So on Monday, or whatever the next day we have school is, I'm going to collect the derivation for the cosine of the sum of the angles, which is posted on Haiku. By the way, do you have the... so, vectors. Now, where do we leave off in our notes? I think we got a little bit into what a vector is. What? They have heads and tails. Did we talk about... Oh, yeah. Okay, in and out of the board. I didn't do that with the other class. And I think I said something about what equivalent vectors are.
Yes. So like if it's like this and you go like that.
That's right. In other words, you can translate a vector, but you cannot rotate it. So now, one thing I didn't give you guys, at least I don't think I did, was these. Did I give you these? Free response question, quantitative question, and your homework. So grab them. Yes, thank you. Yes. So, excuse me. So we talked about what a vector is. Now, let's talk about how you add them. So vector addition. So let's suppose you have a vector u. You have a vector u, and you have a vector v. That's no... What? I hate this thing. So here's u, and here's... I'm done. I am done. This is crazy. This thing doesn't even know how to behave. Here's u and here's v. And so we need to find a way, we need to construct a definition of what u plus v is. And so, definition of u plus v is you take the tail of v and you move it, you translate it to the head of u. Because I'm allowed to translate, right? Based on the definition of a vector, it is an object that has size and angle. So translation is perfectly permissible. So I take v and I translate it over. Yeah. So I take the tail of v and add it to the head . Oh my God. This is fine. It's fine. I take the... What? Wait. Oh no. I'm just seeing things. I'm sorry. So I take the tail of v, I add to the head of u. And then u plus v is going to be the vector that extends from the tail of u to the head of v. So this right here is u plus v. And that's a definition. So now what can we do? Now that we have this definition, what's the first thing we want to verify? We want to verify what would happen if we reversed these? In other words, what are we trying to see? We're trying to see if vector addition is commutative. So does this equal v plus u? So what is v plus u then? V plus u is the vector. Let me copy this and paste it. Here is v, right? And I'm going to take u and do what to it? What am I going to do with u? I'm going to translate it to what? To the head of v. Right? So then what would v plus u be? So this is v, this is u. It would extend from the tail of v to the head of u. And so now the question is, are these equivalent? Yes or no? So why do they look equivalent? Yes. That's right. It is the translation of this vector to this vector. They're parallel. They have the same length. So what does this tell us? This tells us that vector addition is commutative. What else do we need to verify? Is it associative? Because if we know if it's commutative and we know if it's associative, then we're in very good shape. Because we can do a lot with those two properties. So we go, and now to show that something's associative, how many vectors do you need? You need 3. So here's u. Here's v. And here is w. Red, maybe? Unreal. You can't make this up. Here's w. So this is u, v, w. And so, commutative property says what? Excuse me, associative says what? U plus v plus w is equal to? So how do we show that? Which one do you want to start with first? Let's start with this side. So what's that? We take u, copy, paste. What happened to the other what? Oh, God. I'm about to quit. Hello? What type of text? Academic. Go in that thing right there. There should be a book called Hewitt, Conceptual Physics. Got it? And if it's not, it's in the next one, Michael. Yeah, that's it. So this, take care, man. So there's u, and we need to add to it v. So I take v. Of course, v is going to disappear once I do this. You can't make this up. You cannot make this up. Like how? And it's what I love is that it's repeatable. Like it doesn't even have like the audacity to just not do it again. Control C, Control V. All right. So now I'm just going to man it from here. Do you mind? So then this vector represents this right here is u plus v. And it's a pretty enormous line. And so then u plus v plus w, what would I do? I take w and that's right, I translate it and I add it to u plus v. So this oh my God. So this is then u plus v plus w. So this right here. So then what is going to be u plus v plus w? What do I do first? That's right. So I'm going to add v and w. So now let me actually take these two. Let me zoom. I'm going to copy this, paste it, move it down here, take v and w. It'll live. So you can't make this up, man. It's just so infuriating. And so that right there is v plus w. Where did I lose it? I lost the v. Whatever. This is v plus w. Then what do? I take that and I translate that to u. Very good. So I'm going to take that whole thing. Control C, Control V. And there you go. And now, this right here is, what's that vector? Come on, there you are. That vector is u plus v plus w. And what do you notice about that vector? And you can see that it's a translation of the other one. So what does that tell you about vectors? So they're also associative. So associative and commutative, those are great properties. And maybe I should be a little bit more formal about how I write a vector. So, and the reason why I want to be more formal about writing a vector, so you say, let's say a vector u is this guy. So there's u. Sometimes you might want to write the vector. In general, it's a good idea to write the vector with an arrow over its head. That signifies it's a vector. In other words, that's vector, saying that this thing u is a vector. And why did I do that? Why did I introduce that now? Because what happens if I multiply a vector by a scalar quantity? In other words, what does this vector v equals c times u look like? So what's c? C is a number. Scalar is a number, right? So what number do you want to actually take a look at? Say 2. Right? What would 2 consider v equals 2 times u? What would that look like? Yes? That's correct. You take u, right? What am I doing? You take u, and now, does that look about double? So this is 2u, or 2 times u. And of course, what happens as c gets smaller and smaller? What's going to happen to that vector? It's going to shrink, shrink, and shrink, and shrink, and shrink down until c equals 0, in which case the length of the vector is 0, and there is no vector. It's called the 0 vector. But then, You're like, okay, what happens if C is negative? Ah, and so now this is a definition. In other words, negative 1 times V is the vector V is opposite, you could say, the vector V. Or in other words, what does this mean? This means that you have some vector V, and then negative V would be this same exact vector in the opposite direction. All right. So what does this allow us to do then? What is this really? And notice this is equal to, this is defined as, negative V is defined as negative 1 times V. What does this allow us to do? This allows us to define vector subtraction. In other words, U minus V is defined as U plus negative V. All right. So now what does that mean? So if I take two vectors U and V, what is U minus V? Yes. Correct? Correct. So you take V and you flip it. So this is negative V. And then what I'm going to do is I'm going to take negative V, copy it, paste it, and translate it to the head of U. And what do you get? You get this new vector. Get this new vector, U plus negative V, which of course is U minus V. But then someone really, yes?
So what determines which way the vector is facing? So let's say you had U, but then V was something like back that way, and it ended up being on the same.
The vector extends, the addition vector you're saying. That extends from the tail of the first vector you're adding to the head of the second vector. So notice U plus negative V extends from the tail of U to the head of negative V. Any questions so far? Because this looks pretty trivial, right? All right. So now, what do you notice here? Someone might notice something here. You might say, well, Khalil, let's take a look at U and V, because I see something here. I'm going to copy this and paste it. So here's your U, right? And there's my V. And you say, well, what's this? In other words, a vector that connects the head of V and the head of U. You sure? No, you're not sure, right? And you shouldn't be sure. In fact, you should never be sure when it comes to something like this. But there's a mechanism by which you actually find it. You say, okay, I don't know what that thing is, but what am I going to call it? Alpha. right? And what do you notice? You're adding what two vectors to find the third? What two vectors are you adding here by definition of vector addition? Wait, what is it? V and alpha. So in other words, V plus alpha generates U. Notice because U extends from the tail of the first vector to the head of the second vector. So therefore, alpha equals U plus negative V, or U minus V. And notice, what do you notice about these two vectors? And by two vectors, I mean this vector and this vector. They're the same. And so this one I'm giving you is a prescription of how you deal with something called deltas. Yes, my man.
I need
What do you need?
4 academic physics textbooks.
4 academic physics textbooks.
Flying off the shelves.
You're in good luck because here they are. Grab them all. Grab them and go. So, all right. So that's vector addition. That's fantastic. It's really good stuff. And now the question is, what happens if you have a vector U? Enjoy. Vector U, call it U1. U1. U2. U3. And I don't know. They'll live. U4. And of course, what am I going to ask? What is U1 plus U2 plus U3 plus U4? So what do you think we should do? Now, do you think we should go and reconstruct it like this? And the answer is, guess what? You don't need to. Because guess what you can do? I could take U2, translate this, and I can take U3 and translate that, and I can take U4 and translate that. And of course, U1 plus U2 plus U3 plus U4 is, that's right. That vector is U1 plus U2 plus U3 plus U4. And it makes total sense why that would be the case. Because what would happen? You would end up with that as U1 plus U2, right? And then you add U3. And U3 plus U1 plus U2 would be what vector? It would be that vector. And then you take that vector and you add it to U4, and what do you end up with? You end up with that vector. So, any questions? No questions. You guys look so thrilled. It's like you've been sitting in your seats the whole week, and here you are again, and the week's over. Huh? Oh yeah, I mean this is like good stuff, right? This is the whole unit, guys. No, not at all. Come on now. But this is the stuff that you have to have down. You have to have this stuff down. So now, you guys are seeing this. It's pretty obvious to you that this is a highly inefficient way to actually add vectors. Now there's another way called the parallelogram. Anybody know the parallelogram way of adding vectors? If you have a vector u, and you have a vector v, I can take V and translate it over, maybe make a copy of it. So that copy, I'll call that copy V prime, and just write here that V prime equals V. And it's really not that good of a drawing, but whatever. There you guys go. And then guess what I'm going to do with U? Same thing. And notice, what does it form? Parallelogram, and then the diagonal would be that diagonal would be U plus V. And notice, what is the parallelogram method of adding vectors verify? That the vectors, that vector addition is? Why?
Because then you have U and V, U plus V, and then V prime plus V prime.
Correct. All right, so notice this is V added to the head of U, and this is U added to the head of V. Any questions? All right, so that's parallelogram. Clearly, you wouldn't use that either. You're going to lose your mind if you use that. So now we go into the real deal of how you deal with vectors. And of course, how are you going to do this? You're going to map your vector to what? A coordinate system. So what coordinate system do we want to do first? Naturally, the coordinate system that you're most comfortable with is Cartesian. All right, so there's my Cartesian axis. And I really need it for this because this actually allows me to write things kind of really exact. All right, so I'll take a vector U. So here's this vector U. And now what can I do with U? Notice, first off, notice U extends from one point to another point. So looking at this, let's make life easy on us and call this the origin. And let's say these are each one space. 4, 1, 2, 3, 4, 5. And so what's the location of this point? 4, 5. And so the vector U extends from 0, 0 to 4, 5. But bear in mind, that can be translated, right? So it could extend from 1, 1 to 5, 6. So there's no... So now the question is what can you do? So here's U. What can you do with U? Well, one thing you can do is you could say, actually, U is the sum of two vectors. One vector, which is purely in which direction? The horizontal direction, and another vector, which is purely in the vertical direction. So I'll call this UX, and I'll call this UI. And as you can see, U, right, is equal to UX plus UY. And so now, there's a word for this. The word for this is called an orthogonal basis. And what an orthogonal basis is it's saying that a basis is a coordinate system. An orthogonal basis means that your coordinates are perpendicular to each other. And you can see why that's useful. In other words, if you take these two vectors, vector that extends that way and a vector that extends that way, does those two vectors map all of 2D space? Yes or no? The answer is yes. Those two vectors map all of 2D space. Why? Because I can take any combination, any multiple of those two vectors, and match any vector along here. It's like, for instance, if you take this vector, right, you multiply it by -1, what do you get? You get that vector. You multiply it by -2, you get something twice as long. All right? So the question I have is, what about these two vectors? Can those two vectors describe two-dimensional space? Yes or no? Can I describe all of 2D space using just those two vectors? Or combinations of them? And the answer is yes. But it's not convenient. What's convenient? When you have two vectors that are perpendicular. That's convenient. Why is that convenient? We'll see why it's convenient shortly. So, it's called an orthogonal basis. Now, in addition to being orthogonal, what we can do is create something called a norm. And an orthonormal basis, to be technical. And what that means is that what we could do is we can actually say that ux, for instance, how do I describe ux? How would you describe this? Well, you would say it has a length. What's its length? 4? Is that right? So it's 1, 2, 3, 4. So the question is that correct? And the answer is no. What does that lack? It lacks direction. So we need to figure out a way to actually construct a means of telling you that this thing has direction without changing its value, without changing its magnitude. And what you do with that is you construct something called a unit vector. And a unit vector is exactly what it sounds like. What does unit mean? 1. So it's a vector that has a magnitude of 1. So ux is equal to 4 I hat, where I hat means x direction. And the magnitude of I hat is 1. So really, what is that doing? It's just telling me that it's 4 units in to the right. It's in the positive x direction. But wait a second, we're in two-dimensional space, right? So can that really describe that vector in 2D space? And the answer is no. What do you need? Yes, you need the j hat. So in other words, it's 4I hat plus 0j hat, where j hat signifies the positive y direction. And yet again, it has magnitude of 1. And by the way, this means magnitude. Magnitude. Okay. So naturally, what am I going to do? I'm going to ask you, how do you add vectors? So let's see. So similarly, what's UI? Let's see if you guys can tell me what UI is. That's right. It's 0I hat plus 5j hat. And notice, what is u plus y equal? It is, well, if you really think about it for a second, what am I actually doing? I'm describing how you add vectors. In other words, how you add vectors is you add their components. Notice you don't add 4 and 5 and get 9. You add 4 and 0 and get 4. Right? And you add 0 and 5 and get 5. But you have to bear in mind something. How I really verify that, how I know that's true, is based on my other definition of addition. The other definition of addition is this head to tail. And so it makes sense that this is the value of ux plus y, ux plus uy. Why? Because that represents that vector u. Notice, where does u start? At the origin. And where does it end? 4, 5. In other words, it's 4 over, 5 up. So let's go on to next. Now, oh, that's cool. All right. So now let's take 2 vectors. Let's take u, and let's take v. So what is u plus v? What do? Find u plus v. I translate v, so I'll copy it, paste, and I can translate that and notice, what can I do with these guys? Oh, I can do that, but what can I do with each of these vectors? I can find their components. In other words, I could take u and break it up into the following set of vectors. Though that should be moved over. And I can take v, and maybe I'll do that. Oh no. Where? I would choose pink if I knew what color it was. I'm colorblind.
Oh, really?
Yes. I guess.
What's the first color?
Hmm? This is orange.
When you use the drop-down menu,
Mm-hmm.
what's the first color on the left?
That? No, that's black.
No, like on the built-in tent, the second section.
Sure. So this right here is Vx, this is Vy, and this is Ux, and this is Uy. And what do you notice? Well, Andrew notices that, well, wait a second. What you can do, Khalil, is you can use the definition of vector addition to form that vector. But of course, that vector, u plus v, can be broken up as well. This is u plus v. And how can you break up that vector? But be careful, be careful. Let's first break it up formally. That vector is that plus this. What? You just can't make this up, man. Whatever. Like, there's no rhyme or reason to it. And notice, what is this vector? This vector, and you have to be a little careful with your notation. That vector is u plus v, comma x. And that vector is u plus v comma y. In other words, that vector is u plus v. In the x direction, this vector is u plus v in the y direction. And what do you notice about u plus v in the x direction? What is it equal to? U of x plus v of x. And similarly, what is u plus v in the y direction equal? And so there you have it. So now let me ask you, what is the magnitude of u plus v? And it might be a little bit easier to ask you what the magnitude squared is. Correct. So in other words, it is equal to the magnitude of u plus v x squared plus the magnitude of u plus v y squared. Of course, that is just simply Pythagorean theorem. Any questions so far? So now the last piece is, how do you find angles? So like for instance, let's actually zoom in on this guy. How would I find this angle? Call that theta 1. Yes? The sine of that angle?
Sorry, tangent.
The tangent of theta 1 equals Vy over Vx. Likewise, what would you say about this angle? The angle between you. Call that theta 2. Yes?
Why do you have to write it as a tangent?
You don't have to, but generally speaking, what you'll end up finding a lot of times are the components and then taking measures with respect to the components. Does that make sense? Like very few times will you actually have the resultant before the components. But even still, if you do, you could use the other trig ratios. Similarly, what can you say about theta 2? So the tangent of theta 2 is uy over ux. And a little heads up, to be a little careful in terms of how you're defining the angle. And so we kind of need some type of system for defining angles. In other words, I'm going to give you precisely the means or the axis with respect to which we're going to find all of our angles. And that axis is the positive x-axis. And so let's go through this real quick before we continue. So let's suppose this is our vertical. So let's see, from your standpoint. Okay, so from your standpoint, what does this represent? Which quadrant? This is the first quadrant. And so theta is going to extend from what to what? From 0 to 90 degrees. What about if you're in the second quadrant? 90 to 180. In the third quadrant? 270, and then the fourth quadrant? 270 to 360. So everything is with respect to the positive x-axis. Does that make sense? You'll see why this gets annoying. So, all right, so enough of that. Similarly, if I call theta 3 the angle between the x-axis and u plus v, what is the tangent of theta 3 equal to? It's going to be u plus v y over u plus v x. And so just to actually make this a little bit more concrete for people, what's ux and what's uy for this example? What's ux equal to? If you look at this, it's 2 comma, so it's 2I hat plus 0j hat. And what's uy? Is that 6? That's 1, 2, 3, 4, 5. Okay. And then what's Vx? Let me zoom in again. It's 1, 2, 3, 4. 4I hat plus 0j hat. And then Vy is plus 1j hat. And so it's pretty straightforward. U plus Vx is equal to Ux plus Vx. What is that equal to? 6I hat plus. And U plus Vy equals so it's 0I hat plus 6j hat. That's Uy plus Vy, so it's 0I hat plus 6j hat. And so then what is, let's look at the tangent of each of these angles. Let's actually zoom in even further. So then if I wanted to find theta 1, tangent of theta 1 equals Vy, which is what's Vy? 1 over Vx, which is 4. And so notice, I'm just taking the norms of these vectors. I'm just taking the norms. In other words, what's the length of this vector? 1. What's the length of that vector? 4. And it's always going to be that way when you're taking components. Why? Because if you're looking at it purely in terms of components, one of those components is always going to be 0. Similarly, tangent of theta 2 is going to be what? 5 over 2. Tangent of theta 3, 6 over 6. And so then how do you find your angles? Arctan, inverse tan. Any questions? All right, so that's that. Now, maybe you guys should have a little bit of time to actually work on some problems. Should I do that? No, I have one more thing to do. One more thing to do. Let's suppose that I do have that vector. This is such a cool way to do this. So let's suppose I do have a vector. And I know its magnitude. And I know its angle with respect to the x-axis. How can I actually get the components from that? Anyone? So in other words, I have this. I have what the magnitude of u is. And we have what theta is. What can you do? Yes? So first thing you want to do is break it up into its components, right? And what do you notice? Is going to be ui over u. You might even want to say magnitude of ui over u. And similarly, cosine theta is equal to so therefore I can solve for the magnitudes of ux and uy. So in other words, ux, magnitude of ux is equal to magnitude of u times the cosine of theta. And the magnitude of uy is equal to the magnitude of u times the sine of theta. Do I have the vectors? Yes or no? The answer is no, because what do I need to do? I need to give it direction. So ux, the vector, is equal to magnitude of ux. What's that equal to? That's equal to magnitude of u cosine theta. And similarly, uy. And this is I hat. And this is j hat. And of course, what is the j hat component of this? 0. And what's the I hat component of that? 0. All right, that's it. So now, of course, I'm going to ask you a question. Yes?
Why is a magnitude like 2 bars?
That just means it's a norm of a vector. It could be, I could have written it as 1. I mean, this is just the norm of a vector is another way of saying the magnitude of a vector. It's just being overly formal. If you want, you can just use 1 bar. I don't care. But now I'm going to ask you a question. Why is this important? Yes?
Because not all forces are going to be perpendicular to each other, so if we have the direction and magnitude of the force, then we can use vectors to find.
Absolutely. And that's completely correct. And so before we do that, though, Andrew, take a look at this. I can set up a photo gate or a couple of photo gates to actually find the initial velocity with which I'm going to throw that, right? So if you take a look, it's very easy to measure the initial velocity and also the angle. All you need is a couple photo gates and a protractor. And so now, what can you do with that vector? What can you do with this vector? Notice it. You can break it up into its x component and its y component, right? And so, of course, what type of vector is that? What type of vector was it when I threw it? It's a velocity vector. So now tell me, in which direction, the x direction or the y direction or both, is this object accelerating? Let's assume that we're no air resistance. In which direction is this object accelerating? How do you answer that question? Yes. Meaning? Okay. So which direction is this thing accelerating? What do you do to answer that question? No. Free body diagram. That's right. Free body diagram on this. Free body diagram. Toss it. Free body diagram on the marker. So let's look at this trajectory. Everybody knows what the trajectory looks like. It looks like this, right? So take it at some arbitrary point in this trajectory, like right here. Yes? That's right. In other words, she said it's only accelerating in the y direction. Why? Because that's the only direction in which there is a force acting on it. So what does that tell you about this problem? In some ways it is. Why? Why is this trivial? Because if you take a look, right, I throw this, right? I measure this. I measure the angle. What can I do with this? I can decompose this velocity vector into its components. Which components? The x and y components. So I have, let's say, v0, right, which is at some angle. And so here it is, v0. And it's at some angle, alpha. I'll give it theta, whatever. And what can I do with v0? Break it up into its x and y. And then what? Tell me, what's true?
Since it's only accelerating in the y direction, would you only need to apply the acceleration to the y direction of the vector?
That's completely correct. Does everybody hear what Gabby just said? It's only accelerating in one direction. What does that tell you about the x direction? That the velocity is 0? It's constant. The velocity is constant in the x direction because there's no net force acting on it. Therefore, it's not accelerating. Therefore, the velocity is constant in the x direction. In the y direction, there is an acceleration. It's the acceleration due to gravity. And so it's only the y direction where your velocity is going to vary with time. All right. That's it. And that's a primer for this unit, because this is what's called projectile motion. And notice something about projectile motion. Had I done this unit first, right, you would have had to accepted that the acceleration in the x direction was 0. But you wouldn't have understood why the acceleration in the x direction is 0. That's why I did forces before projectile motion. And so now, why is the acceleration in the x direction 0? There is no net force in the x direction. Force gravity is only acting in the y direction. All right. So I'd get started. You should be able to do problems 1 through 6 in your homework on the quantitative questions, and you should also do the physics tours homework as well. And that's due on, I don't know, what's the day after the next Mendham tomorrow? So, Tuesday? I'm adjusting for the Casey.